Good evening, everyone. A very warm welcome to all attendees, our distinguished panelists, and colleagues for joining us for this second session of the Fusion Energy Masterclass series. We are delighted to see your continued enthusiasm and engagement as we deepen our exploration for the science and technology that's shaping global fusion landscape. We are also pleased to have 𝘍𝘶𝗵𝘀 𝘀𝘀 joining us this evening as a panelist. Thank you, sir, for joining, and we would like to invite you to share a brief opening remark before we can proceed to the main talk.
Yeah, good evening, everybody. This fusion is very important program. This is required for the energy security of entire world. So I'm very happy to welcome Dr. Abhijit Sen on this occasion, who is a prominent personality in this field. He will be talking to us on India's progress in fusion program and its global association and roadmap for the future. So I request Samik to take the program forward.
Okay, thank you, Dr. Sharan. So just for a quick recap, in our previous session, we had Dr. Rajesh, who gave a concise and insightful introduction to magnetic confinement fusion with focus on tokamak physics. He highlighted one of the central engineering challenges related to the exhaust heat handling and briefly discussed the concept of liquid metal diverters as a promising pathway. He also touched upon the international developments, noting the growth of the use of high temperature superconductors to realize more compact tokamaks with significantly stronger magnetic fields. In this session today, as Sri Sharan rightly pointed out, we turn our focus to a subject of growing strategic significance. It is India's fusion energy program. Over the years, India has developed strong capabilities from tokamak research and plasma science to a range of enabling technologies while contributing meaningfully to international efforts such as the ITER. The country is now at a very pivotal moment. Decisions in the coming 5 to 10 years on mission direction, on indigenous technology development, advancement of confinement approaches, and partnerships with industry will all shape the country's role in the global fusion ecosystem. So this session will situate India's present strengths, identify emerging opportunities, and discuss possible pathways to future leadership in fusion science. To lead us through this important discussion, we are honored to have Professor Abhijit Sen, one of the world's most distinguished plasma physicists. Professor Sen is an emeritus professor and honorary scientist of the Indian National Science Academy at the Institute for Plasma Research, or the IPR, at Gandhinagar, India. A theoretical physicist by training, he received his PhD from the University of Tennessee, USA, followed by a postdoctoral work at the Oak Ridge National Laboratory. He subsequently joined the early plasma physics group at the Physical Research Laboratory, Ahmedabad, where he played a key role in establishing what later became the IPR. He has served both as the Dean and also as the S. Chandrasekhar Chair Professor at the IPR. His research spans magnetic fusion theory, nonlinear plasma phenomena, intense laser plasma interaction, and dynamical studies of coupled oscillator systems with relevance to biological and neuronal processes. Professor Sen has contributed significantly to India's National Magnetic Fusion Program, where he has served on several international bodies, including those associated with the ITER project. He is a fellow of the Indian Academy of Sciences, the Indian National Science Academy, the National Academy of Sciences India, and the American Physical Society. He has also held visiting positions at leading global institutes, including the MIT and the University 𝘐𝘯𝑥 Marseille. Professor Sen, it's our absolute privilege to welcome you. And thank you for joining us today. And I would now invite you to begin your presentation. The floor is all yours.
Thank you, Samik, and thank you, Dr. Sharan, for your kind invitation and for giving me this opportunity to give the second lecture in this masterclass series of Geo Institute. It's indeed a great honor and a privilege. I would also like to thank many of my colleagues at IPR and ITER India who have provided valuable inputs for my talk today and have shared their thoughts on many of the matters. So, and also as you referred, the first talk, which was given by Rajesh Mengi, set the stage in a very nice way. He gave a brilliant account of the history of fusion and also the basic principles of fusion and the process itself and how to bring about fusion in a confined way. So, and then he talked about the technological challenges. So in my talk today, I'm going to talk more about the science aspects of fusion, specifically about plasma physics and what role it has played in the evolution of fusion research globally as well as in India. And I will focus on the Indian program and describe it in the context of what the World Fusion Program is. So let me start by sharing my screen. Okay, so I'm going to basically talk about the current status and strategic roadmap for the Indian Fusion Program. So here's a brief outline of my talk. I'll start to first motivate the need for fusion energy, and then the current progress in the science and technology of fusion. And then I'll go on to a brief history and evolution of India's fusion program, and then say a few words about how can we move forward from here. So the first point, why does India need fusion energy? That's a no-brainer. As Dr. Sharan says, the whole world needs fusion energy because of the growing demands for energy in the entire globe. In India's case, this need is more pressing because we are in a stage where our economic growth is very fast, and we also need to maintain it in a sustainable and affordable manner. According to the 𝗤𝗏𝘆 𝗧𝗸𝗏 scheme, the plans are to triple the primary energy supply by 2047. So this is a huge demand. The mix of energy that they want to do is to increase the non-fossil fuel capacity to 500 gigawatts by 2030. Also achieve 50% renewable energy consumption by this same year. But the most significant part is that they also need to expand the civil nuclear energy from 8.8 gigawatts to something like 100 gigawatts by 2047, which is a big jump. And they also want to invest in technologies like green hydrogen, battery storage, etc. So here's a picture of India's energy program and the kind of installed capacity that we have and what is the mix of that capacity. As you can see, the bulk of it is still thermal energy, which is fueled by fossil fuels. So we need to get out of that. And there's a major effort in that direction, where we have tried to replace fossil fuels by more greener sources. So India really has made significant progress in this direction. In fact, even before 1930, I think we have achieved this role of increasing our renewables and getting clean energy. However, the problem is that with renewables, you can get clean energy, but it has variable generation. So nuclear power is the only clean energy with a constant base load, and that is our primary need. So India had already thought about this way back, and they put in a very elaborate nuclear program in place, which is the famous India's three-stage nuclear program, which was designed to keep in mind India's modest uranium resources, but abundant thorium resources. So this was framed way back by Homi Bhabha, and it's based on a closed fuel cycle principle. And the first stage uses pressurized heavy water reactors using a mix of uranium-235 and 238, which also produces a small quantity of plutonium-239. So the second stage, which is now being developed, and I understand it's about to begin, is to use a fast breeder reactor to generate more plutonium-239 and energy, and over a time build up the plutonium inventory, and then use thorium as a blanket to then breed U-33. And this will then be used in the final stage to produce very large production of electricity. To speed up this process, there is now talk of encouraging private sector investment in nuclear power projects, including the development of small modular reactors, which is the recent innovation in this field. So where do we start? What is the case for fusion in this context? Why should we consider it? As you know, that fusion has an abundant fuel. The basic fuel that we use at deuterium from seawater, and tritium can be bred in a reactor. So there's no shortage of fuel. It's also very energy dense. It's 4 times as much as nuclear fission reactions at an equal mass. Of course, it is clean, no CO2, no long-lived radioactivity, no risk of proliferation, and it's safe because there's no risk of meltdown. So fusion forms an attractive and strategic component of a net zero energy mix for the future. So this has been known for a very long time. The basic principles have been known, and all these advantages have also been well known. So therefore, fusion has been pursued for a very long time. It's actually been the holy grail of energy research. And there were a lot of false announcements in the past. Like way back in 1951, there was this claim by Argentina's dictator, Juan Perón, was working on a secret research on a remote island, that they had already found fusion. But later on, this research became classified. The famous case is Project Sherwood in the USA. Then around 1955, in the Atoms for Peace conference, fusion was declassified. And this is where Homi Bhabha, as the chairman, made his famous prediction that fusion will be available in 20 years. More progress was made in the late 60s when the Russians started working on a tokamak. And in their T3 tokamak, they announced a 200 electron volt electron temperature, which was the highest at that time, and which surprised everybody. But this was then confirmed by scientists from Kalam and Artsimovich, who actually toured the US, and this established a working relationship between the US and the Soviet Union. So the big question is that if this was so long known and work has been done for such a long time, why is it taking so long? We still don't have fusion, despite Bhabha's prediction in 1955. I think the culprit is, or the spoil sport is plasma. Because for fusion reactions to happen, the fuel of light elements, which say deuterium and tritium, they have to be heated to a very high temperature, greater than 100 million degrees. And at this temperature, the gas breaks down into a plasma, which is a collection of charged particles. And this plasma has to be confined long enough to let sufficient reactions to occur. And this is the condition that you need to get fusion energy. So in such a state, the manner in which you create it, and then you try to confine it, you're taking the whole system far away from thermodynamic state. And therefore, the system would like to relax back to this. You're also creating gradients in all the quantities, density, temperature, current. And this would naturally have a tendency to smooth out. So all these are sources of free energy, which make the plasma highly unstable. So plasma would like to get out of this confined state. And it does so by creating large amplitude and turbulence, which lead to loss of particles and heat. So it is this collective phenomena in the plasmas, which is an aspect which was ignored very early on, when people thought that by just confining the charged particle in a magnetic trap, you could achieve fusion. But once this was understood, then, and this whole subject or whole topic of understanding and taming instabilities began, and this has been the major mission of fusion research over the past several decades. So what are these plasma instabilities? You can think of a fluid where you have these waves. The waves can go to large amplitudes. So you can categorize it by the scale size. So gross distortions, which can arise from large-scale collective motions, are one class of instabilities. Or you could have very fine-scale instabilities, which involve the interaction of these gross waves with the particle distributions. And this can lead to turbulence, and turbulence can lead to a rapid loss of confinement. So you can also categorize it, what is driving this instability. The driving source could be a current, or it could be the pressure, and these can again be of various scale sizes. So some simple examples which have been studied from the early days are things like kink and sausage modes, which are current-driven, and ballooning modes, which are pressure-driven. Here is an example of a kink and sausage instability. Just to give you one example, in the early days, they were studying the pinch experiments, in which you pass a current in one direction, and then this current generates magnetic fields which encircle it, and this tends to compress the plasma, and that was the pinch configuration. But if you now perturb this configuration slightly, for example, pushing it out this way, then you can see that the magnetic fields are more densely configured on this side and more sparsely configured on this side. So the magnetic pressure is higher here and lower on this side. So that pushes this distortion much more, and this thing becomes unstable. So this kind of thing was also manifested in toroidal devices. These are some actual pictures from early pinch experiments. And people found ways of controlling this by putting in a magnetic field or a conducting wall outside. And so this was the early days of instability studies. But these things also show up in the tokamak configuration. In the first lecture, Rajesh had shown how you create a tokamak configuration by a combination of a toroidal current, toroidal magnetic field, and a colloidal magnetic field. And these create very nice nested magnetic surfaces. And the plasma basically is confined by these well-formed magnetic surfaces. So the way the toroidal field and the magnetic and the colloidal field wind around each other, that winding number, the inverse of that, is specified by a quantity called Q. Essentially defines this twist that you have in the magnetic field line. So it depends on the ratio of the minor to the major radius and the toroidal field and the colloidal field. So it's proportional to 1 over the colloidal current that you, or the plasma current that you generate in the toroidal direction, which is what creates the colloidal field. So this factor Q, which is a continuous function of this kind, which is increasing towards the edge of the plasma in a tokamak. There are certain surfaces here which are called rational surfaces, where m and n are integers. And these are very fragile. This is where, if you disturb those surfaces, they can create an instability there. So one of the earliest studied and most widely studied such an instability is the sawtooth instability. This is a kink instability that takes place at the Q equal to 1 surface. And basically it's thermal instability. So as you keep on heating the plasma, then the current at the core of the plasma keeps on increasing, because as you remember, the current depends on the collisionality. And as you heat it, the collisions go down. So the current increases, therefore Q starts going down. If it goes down below 1, then it triggers an instability. What happens is it starts forming these islands. So, and as this instability, it steepens the gradient there, and that triggers an instability. And you can see which is a kink instability. This is what's growing there. And as the island finally hits the surface here, it creates this whole gradient is relaxed and it crashes. And therefore, the form of this instability, or the waveform that you observe, either in temperature or density, has this sawtooth-like form. So it rises slowly and then crashes. So by themselves, they are not very bad. They're called internal disruptions. And if they're kept at a reasonable level, then they actually eject impurities from the core of the plasma. So it's like a burping of the plasma. But if they become very large, then they can cause problems. Also, in that case, they can also trigger other instabilities, and something that's called a neoclassical tearing mode, which I'll describe very briefly. Then there is something called the classical tearing instability, which occur at the other mode rational surfaces, like the Q equal to 2, 3, 4, etc., or even 3 by 2. And what this is that at those surfaces, if you create a perturbation in the magnetic surface, then they slowly start growing into an island. That means the surface is broken up, and you can imagine the fields being cut and reconstructed to form an island. So that's the form you see here, that these are little, from the nice circular nested surfaces, in one surface you start developing a magnetic island. So along this magnetic island, because the particles are traveling very fast around the toroidal direction, so the pressure becomes flat in those directions. So that can degrade confinement. If these islands go very large in amplitude, then they can also interact with each other. And so islands developing two surfaces can, for example, non-linearly interact. And this create a very major perturbation in the plasma, leading to something called a major disruption, in which the current suddenly is totally destroyed and all this energy is sent to the wall. This is what Dr. 𝗏𝗍𝘆 had also discussed in his talk last time. So the basic physics under it is this whole business about reconnection, in which the field lines are rearranged. And this is governed by the plasma resistivity at those particular rational surfaces. It's normally a very slow process. And therefore, if you do not have a long-lived plasma, it may not pose a great threat. And you can normally control this by actually modifying the profile of the current. But when you go to very large, very high temperature plasmas, then there is an analog of this, which is called the neoclassical tearing mode. Neoclassical in this sense means that in a toroidal geometry, you have another class of particles, because as you go along the magnetic field, and because the magnetic field is decreasing from the outer edge into the inner, you can have a mirror-like configuration. So some of these particles can get trapped in this mirror-like thing, and that can give rise to a current, which is called the bootstrap current. Bootstrap because it depends on the plasma gradient itself. So the plasma is self-generating this current, which is really a good thing, because then you can reduce the current that you are imposing from outside. But these instabilities can actually reduce your confinement by a great deal, and therefore they can really limit the amount of pressure that you can hold in the plasma. This is a quantity called beta, and therefore they are a major concern for all reactor grade machines. And if they grow very large, they can also create major disruptions. So control of NTMs has been a major research effort over the years. And basically the idea is that because in this current, within this island, the bootstrap current is lost. And that's what creates this instability. So one way is to restore the current within that island. And the way people do that is to first locate the island and then drive an external current through it using a localized electron cyclotron current. So this is a current drive mechanism, and that can restore the bootstrap current, and again you can heal the island. So this is a well-developed technique now. Another class are these pressure-driven things. These are called ballooning instability, and the name comes from the fact that it's as if the column is ballooning on the outside. If you look at the analogy for air in a tire tube, then as you put in more and more pressure into this tire tube, because the outer surface of the tube is vulnerable, because the material has stretched to a larger extent on the outside than the inside, and therefore you can sometimes create a bulge on that side, and that's like ballooning of the thing. A similar thing can happen here, because the outer side of the tokamak, because the magnetic field lines are again sparsely spread out compared to the inner side, they are a weaker surface, and therefore they can again the plasma can balloon out through that region. And these take the form of plumes or fingers, and therefore this is another reason why you can limit the plasma pressure. Finally, they could have a combination of both current and pressure driven. And Dr. 𝗏𝗍𝘆 had spoken about this thing last in his talk. These are these edge localized modes, or ELMs. What happens is that when you heat the plasma, it can, in a tokamak, the tokamak can suddenly go into a higher confinement mode, which is known as the H mode. And this happens because you develop a barrier at the end. And this happens by actually shrinking and moving the profile, both the current profile and the pressure profile, for example, inward. And there's a steep barrier is created, which actually limits the loss of energy from the core. So this is like heating if you think of a pressure cooker where you start heating from outside, and so this transport barrier is like the lid of the vessel. So if you heat it extremely highly, then this whole barrier can explode. So the lid can take off, and you would have an explosive instability, or in this case, a major disruption. The way out is to actually leave a little hole or a little space in the lid so that you can put a little spoon under that thing, so you can leak out the energy. And this is done in a tokamak by actually having external resonant perturbations, which actually create little islands, which are like holes in the magnetic surface. And these leak out the things. So that is how you control ELBs to a reasonable level so that you do not put too much energy onto the wall of the tokamak. So this instability is very similar to what happens on the solar surface, and this is a picture of a solar flare. So everywhere you see the connection between the basic plasma physics that occurs in a tokamak device or in the astrophysical context. So as I said, control and mitigation of instabilities has been a major thrust in plasma physics. The instabilities I discussed are called magnetohydrodynamic instabilities. And these have been combined to controlled to a combination of in-vessel magnetic coils, localized current drive using at various frequencies. And then if everything else fails, you also have a disruption mitigation system using massive gas injection so that you can radiate away the energy, or using shattered pellets. Now, these things have made great progress in recent times through the use of AI and ML, because our machine learning methods. And the basic idea is that if you build up a large database, then you can collect all the data and actually try to evolve an algorithm which will detect from beforehand when will a disruption occur. And this has been a major improvement in the control of tokamaks. So this is just to show that how simulations have helped in shaping the tokamak profiles and improving confinement. So all this has led to, this is like controlling a tokamak plasma is like actually flying an airplane, but you really have to have real-time control of several features. So this is just a diagram to show how you're controlling all these features in a tokamak. So all this research over several years have led to many key empirical findings for tokamak stability, basically defining what the limits are of these quantities like Q and beta, which has actually defined a safe parameter regime for tokamak operation. And this is what has helped the development of all these results and the progression of tokamak performance. Over this many years, ever since ITER started, and there was also a special group that they formed, which is called the International Tokamak Physics Activity, which is an expert group drawn from various countries who actually, they were the ones responsible for defining the physics basis for the operation of a tokamak, physics basis for the design of ITER. And now over the past few years, they've actually improved this and extended it to the operation of a tokamak when it goes into the burning plasma. So there's been a series of articles in a special issue of Nuclear Fusion, highlighting all the critical issues, major areas of progress, and most significant recent results. And this is an excellent reference material which I would recommend for students. It's also very good for experts to find out what is the recent state of affairs. So based on all this understanding and of plasma physics and instabilities, tokamaks have made a phenomenal progress over the years. And you can, this is the ion temperature that they've obtained, and this is the triple product, which actually is a figure of merit and on the way to getting fusion. So this is the la la land, or where you want to be if you want to get a fusion reactor going. And as you can see, ITER will probably be around here with a Q of 10. But you can already see that machines like the JT60U or JET JT60U are very close to this line of Q equal to 1, where you could have a break-even condition. So these are some of the highlights of the tokamaks. Like JET had obtained 69 megajoules of fusion energy in a DT experiment late in 2023, after which JET was shut down. EAST, which is a Chinese computer, they obtained a record pulse length in their plasma of something like more than 1,000 seconds. K-star also sustained plasma at over 100 million degrees for 48 seconds, which is a record. And JT60U has a record triple product. So against this background, let me come now to the Indian fusion program. There's a bit of prehistory. You've all just told you about how Homi Bhabha was the very first strong advocate of fusion energy. And his presidential remark, which was over-optimistic, but it's succeeding in opening up fusion research in the world and triggering a whole worldwide activity. So he also himself set up an experimental program on a theta pinch. Theta by theta 1 means that the current now is in the polarity direction in TIFR. And this was a very nice program, but unfortunately it was wound up in the early 60s due to some adverse publicity that fell out of a UK experiment of a pinch, which was zeta. And therefore, it was felt that fusion is not feasible. The next major attempt was in the early 70s, and Dr. Sarabhai formulated a plan for the development of plasma physics in order to strengthen the space physics program that he had already initiated in PRL, and also to lead eventually to a fusion program. So he actually handpicked a team of scientists from India and abroad to form a core group at PRL, and this included Professor Pradyuman Kaur. So during 1971 to 75 was a very exciting period that actually built the bedrock for the future fusion program, because it led to the starting of many basic experiments to develop experience in plasma physics, skill building, and experimental experience. It also started a vigorous graduate program within PRL in order to generate future manpower, and generated some excellent young people who later on went on to do a great deal of work abroad. So in a sense, this was the dawn of a new age of plasma physics in India. But unfortunately, it did not lead to a fusion program at that time, because Dr. Sarabhai died in 1971 prematurely. And after that, although we continued with this program of building a plasma physics group, one could not initiate a fusion program. There was no funding available for that. So people like Professor Kaur went back to Princeton from where he had come. So there was this long hiatus between 75 and 82. During that period, there was a strong upsurge of fusion activities in the world, particularly in the US, and tokamak performance were improved everywhere. So there was renewed hope for fusion, and many of plasma physicists abroad, who used to meet regularly at these conferences, had long and intense discussions whenever they met. And so a decision was taken to initiate a program in India and to submit a proposal on the tokamak device to the government of India. After a long chase of about 4 years from 1978, this finally saw daylight. And a DST-supported independent program was started at PRL. And this started with a tokamak design with an early approach, which was later modified when Professor Kaur returned in 84 to assume directorship of the project. So this was an ambitious design, but enabled exploration of the latest tokamak advances. The idea was that, we had lost some time while tokamaks in the world had made such progress, So this was the leapfrog approach that we took, and that is how Aditya was born. As you can see, the name reflected both the optimism of the day and our future ambitions. We're trying to create a sun on earth. So here's a picture of the Aditya tokamak at the Institute of Plasma Research. Its first plasma was obtained in 1989, and this has been the workhorse of tokamak experiments at IPR since then for over the last 25 years now. So it's a medium-sized tokamak of 75 centimeters major radius and 25 centimeters minor radius with a magnetic field of about 1.45 Tesla and a current of 160 kiloamperes. The densities are in this region, and the temperatures that we have obtained at the maximum is about 600 eV. So Aditya, right from the very beginning, explored many frontier areas of plasma physics and fusion physics. One of its earliest success was the discovery of intermittency in the edge transport, which showed that the transport in the edge was not a continuous phenomena, but happened in bursts. And this was a new phenomena which was then replicated by many other tokamaks. Then there were experiments on density limit experiments, all those parameters that I've showed you earlier, which actually define the safe parameter regime for any tokamak, depending upon its intrinsic parameters and the density and temperature that you can get. So an important experiment that in the later years that Abhijit undertook was the study of runaway electrons. These are very fast electrons which can get generated when you have a disruption. And these can be very harmful. They can actually puncture holes in your wall. And then how to avoid disruptions and how to mitigate disruption. So these were contributed to the ITPA disruption database. And this was an important contribution from Aditya. Around the same time that Aditya was formed, there was also another tokamak that came up in the Saha Institute of Nuclear Physics. This was a commercially built device, which was built by Toshiba. And in this experiment, in this device, some very basic and nice experiments were carried out. For example, sawteeth were widely studied on this. They also explored regimes like with very low Q discharges, biasing experiments for improved confinement, and tested out a number of diagnostics. One of the nice things they did was to produce excellent trained experimentalists, some of whom then later joined IPR and have been the major contributors of the Aditya tokamak. This tokamak is not operational now, and actually it's been shut down. Then in 2015, it was decided to upgrade Aditya to improve its capabilities. So this was done in a rapid time of about 1 year. And so basically what was changed was we got a new vacuum vessel and also new diverter coils. So Aditya didn't have a diverter configuration earlier, and some other hardware changes with that. So with Aditya U, again, a number of experiments which were at the leading edge of tokamak research in the world were carried out, including a deuterium plasma operation and some development, some novel approaches towards disruption control, and then runaway electron mitigation, and also very nice pellet injection experiments. A very nice pellet injector was developed in IPR, and this was tested out on Aditya. So to summarize, both Aditya and Aditya U served as rich physics research devices and also provided experience in handling a number of tokamak-related technologies. And the other nice thing is it trained a number of students and technical personnel in this area. The next big step happened in 1996 when we got the approval for building a superconducting tokamak, which was named SST-1. This was a state-of-the-art superconducting steady-state tokamak, which had features like shaping the plasma and a diverter. It was designed for a 1,000-second pulse. So at that time, it was in the same class as East, K-star, and JT60, which were just coming up at that time. It was not very large, just slightly larger than Aditya. It was 1.1 meter, but it had a very high magnetic field of 3 Tesla and the superconducting magnets, so it could, the hope was it could maintain the plasma for a very long period. It had a lot of capacity for heating and current drive at various devices using lower hybrid or ion cyclotron resonance heating and neutral beam heating. So on this device, the first plasma was obtained in September 2013. So here's a summary of SST1 technical and physics achievements. One was that it was able to energize the magnet up to 2.7 Tesla, which is almost 90% of the design value. It achieved plasma current of 100 kiloamperes. It was not up to the design value yet. And it also was able to integrate and reliably operate this liquid helium cryo plant at full capacity. And this was one of the biggest plant capacity in India. Then all this experience with ultra-high vacuum systems. This was the largest toroidal vacuum vessel in India at that time. So it also demonstrated lower hybrid current drive in its phase 1 operation. So it ran something like 29 experimental campaigns till June 2023. But during these campaigns, intermittently it faced technical problems related to the superconducting magnets, the cryolines. So there were leaks that developed the cryostat and the SC magnets and the cryolines. So eventually one had to stop these campaigns and attend to these problems that we were facing. So this has been thoroughly analyzed, and a decision was taken to refurbish the SST tokamak. So this refurbishment process has already started, and the phase 1 of refurbishment has been completed. So now they have started machine cool down, and it's expected that SST1 will resume operation shortly. There are also plans to upgrade all the other subsystems of the machine. Finally, the next big step, that India became a partner in ITER in 2005 as a full partner, which was actually a significant recognition of our scientific and technical competence. It was also a major boost and upscaling of our fusion program by integrating our program with those of all principal global fusion niches. So this became an opportunity to become a key contributor and a beneficiary in the cutting-edge R&D of tokamaks. It also provided a global platform for Indian industry, both public and private sectors, to participate and contribute to the construction of ITER. So here's a picture of ITER, which is the biggest tokamaks to be built, and it's making good progress, as you can see, and it's expected that should be operational in a few years. So India had the responsibility to supply about 10% of the major procurement packages that ITER needed. So here are some of the packages described here. If you look at the cryostat, which is the biggest cryostat in the world, or the biggest vacuum vessel that you can think of, and this was one of the things that India was assigned to do. So the thing is, many of these packages involved first of its kind technology and involved also R&D to actually accomplish those technologies. So this was a major challenge, which actually I think benefited us a lot. India has now more or less delivered most of the packages that it had undertaken. Here's an example of the cryostat. It's a huge device, as you can see. It's from 3,850 tons. And this has been delivered and is being assembled in ITER. It also developed very high voltage power supplies and ITER distribution lines, which is under manufacturing. So these are the lines that are being installed in ITER. But another big advantage of participating in ITER was that it set up R&D facilities in IPR in order to ensure ITER deliveries. And these are highly sophisticated test facilities, for example, for neutral beams, IC heating, electron cyclotron heating, and have been created in a special lab for ITER-related developments in IPR. So these test facilities will qualify and establish that the deliverable parameters for ITER are reached for each of these subsystems. So here's a summary of what have been the benefits for ITER operation. It's in both scientific as well as industrial. It has given significant R&D programs in IPR, which are focusing on cryogenics, heating systems, development of diagnostics and modeling, support for nuclear analysis. It also has led to deputation of Indian PhD scholars and young scientists to ITER, and it has trained some manpower in the way of Indian personnel in ITER. It's also been a big boon for Indian industry. Indian industries have acquired competence in manufacturing that meets demanding international nuclear quality and safety standards. And some major Indian industries have actually participated in fulfilling these ITER packages that India has been asked to deliver. So both Aditya SST-1 and ITER commitments have led to establishment of technology development programs whose scopes actually go beyond these machines and are aimed at a long-term fusion program of the country. Some examples are in magnets, radio frequency heating, or current drive, neutral beams, and plant systems. Also, programs in critical areas that are relevant to fusion have been set up within the Indian R&D and industrial setup. For example, work on fusion-grade materials, tritium fuel cycle, which is part of the DA program, and large-size reactor components. So that is our state today. And where do we go from here? That is the main question that we need to address now. So the usual path to a fusion reactor consists of these three important stages. One is the stage when scientifically you achieve break-even, which means you satisfy the Lawson criteria. And this can be done only through making progress in plasma parameters and confinement time so that you finally come to and control of the plasma. After you achieve scientific break-even, you can design and demonstrate a demo device where you use all this scientific expertise, but also you prove the engineering feasibility and establish that it can generate energy, that all the engineering design is such as so that you can go on to a machine which will actually deliver electricity to the grid. So these are the three major steps. But the most critical step is this, and from which, how do you project to a demo? So let's see what other people have done in this respect. What are the global projections for demos? If you look at the major parties, for example, the European Union, this is banking on ITER to demonstrate break-even. So that is their break-even machine. And they have participated and also sponsored ITER to a very large extent. So ITER plans to start operation in 2035, which is their latest prediction. It will commence DT operation in 2039 to achieve break-even. So EU is planning its design activities to start around 2027 and construction in 2040 and operation in 2050. And therefore, and after that, of course, a commercial reactor in the second half of this century. That is the usual conservative path to a fusion reactor, which actually EU is following. Of course, EU individual members have their own fusion programs, comprising several tokamaks and other devices spanning several decades. JET has been one of their star performers in this, as I showed earlier. Next, you come to USA. It's one of the longest history of fusion research with several experimental devices. Their program has actually gone through several ups and downs in the past, but they have a tremendous record in achieving good plasma progress. And their program is spread over national universities, national laboratories, as well as universities. However, presently, it is being driven aggressively by private companies that are aiming for fusion reactors in the 2030s. That's a big change from the conservative approach that people were earlier thinking of operating in the 2050s and the second half of that. So they want to leverage recent innovations like high temperature superconductivity, which can create compact devices, advances in AI, which can help you in construction and in controlled things, and high computing power. So this cuts down on design time and also creates things like digital twins on which you can do several experiments without actually having to do a physical experiment. Then we come to UK, which also has a long history of fusion research. Remember Zeta, and has benefited strongly from JET. It has launched an aggressive program now, which is based on a variant of the usual tokamak. It's called a spherical tokamak. And this is called STEP. And they have entered this project in a public-private partnership mode. And they plan to have a demo again in the early or late 2030s. Japan likewise has a very strong domestic program. In fact, they have made a strong bid for ITER and in various magnetic configurations, including tokamaks, accelerators, etc. But they have built their program with strong collaboration with EU. In fact, this is what helped them to develop this JT60U from their earlier JT60 machine. And this was called the broader approach, in which they not only shared their technical and scientific expertise, but they also shared resources. And therefore, they were able to build this machine very quickly, and this is now performing extremely well. They also aim for a demo in 2030s, and they want to do it in collaboration with UK. They have declared UK to be their partner in this effort. Korea, which has always had a very strong collaboration with the US, and US helped them in building their K-Star tokamak. So they are planning an operation of the K-Star for a demo in 2050. Among all these nations or parties of ITER, China has made the most spectacular progress over the past few decades. They've done it through a series of devices that were either built or machines that were adapted from elsewhere. For example, they took over all these Russian series of HT machines and converted them in China into their own machines. Similarly, they took TEXT, which was a small device from the US, and they started their university program that way. So over the years, they've had active collaboration with US, Japan, and EU. And after establishing record performance on East, they have now an aggressive path to demo. They have already started building a burning plasma experimental steady-state tokamak, which will achieve DT-Q of 1 for 1,000 seconds in 2029 to 2030, and will eventually get to Q of 5. So they are not dependent on ITER operating. They have their own plan, and they're confident that this will give them a demo in the fastest path possible. And this is just to show an example of how strong their domestic program has been, the number of tokamak that they have operated, built, and used, including in the national labs as well as university experiments. And in the process, they've built up a massive scientific power, manpower. So what are the key takeaways from these major programs? One, of course, is they have very strong domestic programs, which are based on a series of successively larger and advanced devices, which are spread over national laboratories as well as universities. They have strong linkages with industries to advance technology development and establish a supply chain. The well-planned trained manpower development programs through involvement of academia. All of them have had major international collaborations, both bilateral as well as multi-party. In recent times, because of this great upsurge in private funding of fusion research, by recent estimates is approaching $10 billion now, and also based on all these technology innovations that have taken place, all these parties have a willingness to adopt them in their programs and accept these innovations and move on a faster path. So given this background, what is the path we need to follow? And that is the question I would like to address next. But for that, we need first to take a realistic assessment of where we are today. I've come back to this diagram again where I've shown all the progress that fusion, that tokamak research has done. On this diagram, we are way down here. This is where Aditya is, and this is where SST1 is at present. If we are able to operate SST1 to its full capacity, then we might make a progress here. But as you can see, from this point up to the point here, there's a long gap, and so we have a lot of catching up to do. So the question is, can we afford a long-drawn scientific capacity building program? So again, as was done in the past, one can try and look at a rapid path, something like a leapfrog approach. And the idea is to leverage our present scientific experience in building and operating Aditya, SINPT, and SST1 to actually do a leapfrog to an accelerated path to fusion. So what is an accelerated path? Supposing we try to build one machine between our present state and when we get to a demo. So that machine could play the role of 𝗏 that is playing for EU. So in order to do this, we can try to use present innovations like high temperature superconductivity and AI to design a compact field device that's a lot cheaper than 𝗏, but has design features that ensure good stability, fuel breeding blankets, long pulse operation, etc. All of this folded into one sophisticated device, which will take us to a demo. So keeping this kind of a philosophy in mind, a conceptual design is being considered and worked upon. This has been named as SST Bharat. So this is a device which is about 2/3 the size of 𝗏 and has correspondingly a lower Q factor of fusion amplification of 3 instead of 10. So the volume is much less. And because the volume is much less, the cost is a lot less. And the pulse length has been kept at 300 seconds and 3 hours in TT. So this is a preliminary design that's being discussed and debated in the community. The estimate is that this could take 5 years of design and 10 years of construction. That would really advance us in this way to a demo. So this is a conceptual proposed roadmap. As you can see from SST1, like to go to this SST Bharat, which can lead on to a demo. So this would put us into the 2050s or 2060s, and then you'd have a reactor after that. So how do we analyze this machine and this roadmap? I think it is a good goal to have, but as you can all see, it's a giant stride that needs to be broken into small steps in order to be a practical path forward. So what is the primary constraint that we have? I think the primary constraint is the lack of sufficient expertise and experience in producing, controlling, and diagnosing progressively hotter and denser plasma. We have done very well with Aditya in all these areas that we wanted to do, but Aditya has it's a limited, it's a small machine, and you can only have a density or a temperature up to a certain extent. So you cannot go to that region where all these things are possible. So unfortunately, there is no shortcut for that. We need to expand our domestic program to provide for a broader experimental base. And most important, we need to create a large pool of trained personnel to participate in the scientific capacity building to get to a demo. So these are the demands that we have on our program. Now, how do we go about that? I'm just listing here a few intermediate steps that need to be taken in parallel for capacity building. We cannot do all of this in a sequence because then we will be really late in getting to a demo. So keeping the time constraints into mind, how do we overcome some of these other constraints that we have? So we have to, first of all, initiate a vigorous and extensive manpower generation program. This can be done through seeding experimental plasma centers at universities, such as at Geo University, for example, and of course all the IITs and other universities that we have. We need to actively bring back past trained manpower from abroad, many of whom have been trained in IPR earlier and are now working at the leading fusion centers in the world. Then we have to make plasma science a mainstream university subject. The analogy here is what nuclear physics became a mainstream subject of universities during the early days of when the nuclear power program started in India. And the power program benefited a lot from having all these people trained in nuclear physics. Second, of course, we have to build larger size tokamak, 1 or 2 or more, with conventional technology like copper-based magnets. One example is to have a D3D type machine, which has been built by General Atomic, at one of these centers, such as, and I think Geo University comes to mind. We could have it in a public-private partnership model. And they can take this. This would be a way of actually nucleating a program in the university environment and using private partnership model. This can be further strengthened with the involvement of additional private industries. We have to accelerate the IPR program. For example, the refurbishing of SST-1 and other things through bilateral international collaboration programs to undertake specific science technology training programs. We need to open up. Finally, we need to strengthen our partnership with industries to not only generate technology and speed up development, but also to raise resources. And I think many of the private industries would be willing to contribute to contribute resources for the development of our Indian program. Finally, and these are my personal thoughts, in the long term, I feel that if our program has to succeed, then we need a national fusion policy with an institutional framework. So to ensure overall success of the fusion program, we need to put in place an official policy and a national plan to ensure long-term commitment and thereby provide stability to the program. This was done both for our nuclear energy program and also for our space program, both very successful long-term projects in our country. They were conceived at a time when our state of preparation in each of these areas was not very different from what we have now in terms of what can be done for nuclear fusion. But there was a vision that this was important for the country and that this had great utility for the development of the country. And keeping that in mind and keeping the constraints of the country in mind, a long-term national plan and policy was put in place. So along those lines, we need to have a national fusion policy and with an appropriate institutional framework. Such a plan would provide a vision and a blueprint to guide us in our quest to exploit this rich source of energy. I think because given our state of preparation, we have the talent, and given the state of upsurge in fusion activity all over the world, I think this is the right time to do it. And I think we should not miss this opportunity. So let me end on this wishful note and on hope for the future of fusion program in India. Thank you very much for your attention.
Thank you. Thank you very much, Professor Sen, for that very thought-provoking session. We have some questions, and I would like to relay that to you in the order that they came in. So the first question is related to your thoughts on what role should India take in manufacturing high-temperature superconducting tapes for fusion. I think in one of your takeaways you mentioned this as a key takeaway. So he wants to know about your thoughts on developing superconducting tapes.
Yes, thank you for the question. I think it's a very important question, and we should be undertaking this development process. I think some initial work was already started at BRC, but we should take it on a larger scale and involve industries in doing that, because that will form a very important component of our future program.
Okay. So the second question is, how non-thermal plasmas will help in the case of gas conversion in industries in India?
Oh, you mean by gas conversions, you mean?
Okay, I'll let the person type in a little more detail. So I'll take the next question. This question is from Rajesh Shetty. If you can just elaborate so that the speaker can better understand what exactly you are asking. So then there is a three-part question, and it's related to, and I'll combine it. It's related to the role of IPR. So it's asking that many countries like the US have changed their safety regulations for fusion as compared to that of fission. And in India, still such effort is missing. So how can IPR take the lead in this? His second part is again related to fundings from the government of India. There are talks about small modular reactors, but nothing so much on fusion yet. IPR being the lead institute, how can they help in addressing this issue? And the third part is, like, there are several private companies in India which have started focusing on fusion energy, and how can IPR support this kind of ecosystem where research and with industrial partnerships and government, like this trilateral partnership, how can IPR play a role in these three?
Okay, so let me come to the first question. In fact, part of my appeal to the policymakers for framing a national policy and putting an institutional framework is that such an institution, which in the case of the nuclear energy program is the Atomic Energy Commission. In the space program, it is the Space Commission. It is their job to actually work out the framework and for safety and regulation. This is what is being done elsewhere in Europe also. France, for example, while ITER was being built, they worked on these regulations, and US is also trying to relax that. And I think there's in India, there's an attempt to do this for the regular fission program. So in order to do such a thing for the fusion program, you need to have a proper institutional framework. Your second question was on
government funds.
Government funds, yeah. That again, that's why I've used this word, that you have to ensure long-term commitment and provide stability. And that includes regular funding and an assurance about funding, which can again be provided by if we have a commitment at a national level. The third one was private industries. Yes, I mean, that is something that we would like to encourage. We are aware of a few startups that have been formed in India. They are mostly involved right now in doing computer simulations, which we would like to encourage. And as I mentioned my previous thing, that they are the ones who can also get involved in things like this when we start a public-private partnership model. So, for example, in this geo venture, we could involve some of these startups to aid in the design and in developing some of the control systems.
Okay. So again, there is a two-part question. So India's fusion energy program is often highlighted as a pathway to sustainable energy security. How do you see artificial intelligence, machine learning contributing to real-time tokamak plasma control and disrupting mitigations?
Yeah.
And what are the key challenges remain for India in scaling this technology towards fusion-based sustainable energy?
Yes.
And he has a second part. I can relay that to you once you answer that, or I can.
Okay. I think as I mentioned it very briefly in my thing, that the role of AI and ML is in two main fronts. One is that it can really help you in the design of the machines. They can also help you create what are known as twins, or tokamak twins, which are actually computer simulations of an actual, where you can actually change the parameters and see how this machine performs. So, and ML actually helps you by developing these algorithms or these models, which are based on past data that you have generated from various experiments. So India is actually investing in that. Even at IPR, we are developing all these computer models to deal with this situation. And this is something that needs to be developed to a great extent. We have the resources for that, certainly the talent for doing this kind of thing. And we are also trying to build up our computer resources by actually installing very large computer systems in the country, including there are proposals for doing that in IPR.
Okay. So his second part was that ISRO has demonstrated indigenous cryogenic engine capabilities for space research, and fusion energy is now seen as a critical pillar for sustainable energy. So how do you see, let's say, parallels where AI and ML could play an integral role in advancing fusion reactor performance, particularly in predicting instabilities and ensuring plasma stability within India's long-term fusion roadmap?
Right. So as I mentioned, I mean, it can certainly play a very important role in prediction and control. That's what's being actively done elsewhere in the world. Basically, on the basis of large amount of data that has been obtained over a large number of tokamaks, they have developed algorithms which are based on AI and ML techniques to build these prediction models, which can tell you, given a certain parameter configuration or given certain symptoms that you observe in the evolution of the tokamak discharge, you can almost say, and this has now come to a stage where they have a prediction capability of over 90%. You can say that now disruption will happen. And therefore, you can then you can put in your control machinery into operation and actually either quench that thing, or if it does happen, you can nip it in the bud or prevent even it then taking place altogether.
Okay, thank you. We have many questions. Okay, let me see. So I think there was one question from that what are the main reasons for us, like, let's say, falling behind? As you said, there is plenty of catching up to do. And I think, is it the availability of funds? I think you mentioned some of that in the last slide, where you need to come up with a fusion policy. You highlighted the fund issues from the government. You highlighted how we need to bring back people who have already had the training and expertise at IPR and now working abroad. Or is it the limited capabilities of our scientific community? So I think you touched upon some of them, but if you want to add something to it.
No. So, I mean, delays are inevitable in any big project. I mean, it's not just what has happened to our fusion program. It has happened in other programs as well. And this is part of any big project and part of evolution. You must recall, for example, if you take the specific instance of SST-1, this was a new technology for us. It was the first time that one had built a superconducting tokamak from scratch and using indigenous capability and expertise. So, like in other major projects, there are bound to be hiccups, and that can lead to delay. So I would only call them minor setbacks, not a failure, but it's a learning step that one has to inevitably go through in order to proceed. So one is still hopeful that SST-1 will be revived and will start performing, particularly after all this refurbishment package that we are implementing.
Okay, thank you. So the next question is about SST. There you mentioned that there are some technical issues with SST. So the question is, how can we ensure that the same issues are not repeated in SST Bharat? What are the steps that are being taken?
Yeah, so that is why we need to establish a good expertise and a learning experience.
Okay.
And that was the whole thrust of my saying that we need to broaden our physics program or scientific program so that we can get experience on various machines. And also, I think, like in other programs, we need to have strong collaborations to enhance and enrich our knowledge base. And at the present time, fusion research is still relatively open. It is not classified. People still share knowledge. I give you one example of ITPA, where experts from all over the world have really exchanged their knowledge and created expertise in it. So we have to encourage collaboration and build up some of this knowledge around it so that we do not encounter serious problems with SST Bharat.
Thank you. The next question it's related to the fact that is India planning to get into any other major international collaborations with countries, let's say like South Korea or France, to design and build the next SST upgrade? And wouldn't this kind of collaboration, apart from ITER, would help us in leapfrogging? I think you mentioned leapfrogging several times into the R&D aspects of the design.
Yes, I think it's a very, very nice question and suggestion. We do not have any plans of building future machines in collaboration with other parties abroad, but that's certainly a good possibility, and that's something that I'm also advocating in order to speed up our progress in this direction. Now, whom we chose and how do we do it is a question of detail that needs to be worked out. We already have MOUs with several of these European countries, EU, for example, and also UK. And so we could probably, invoke some of these to proceed in this direction.
Okay. Okay. So there is another question related to the fact that from Aditya to SST, what do you see is, let's say, our biggest achievement in the fusion front?
Oh, I mean, the fact that we went from Aditya to SST, Aditya itself, the biggest achievement is all the physics that we have learned. And not only about plasma physics, but how to control, how to produce a plasma of a certain parameter regime, how to control it, and then how to diagnose it. And that has been the major. And in doing so, I think Aditya has contributed to some of the leading physics questions in the tokamak physics area. And I think that is the biggest thing. SST1 has been a major step in technology learning or technology mastering, particularly of the superconducting magnets, and in trying to obtain a long pulse experiment. Unfortunately, it's still not operated yet, but once it does, then that will be a major achievement, because you need, in order to get to the break-even point and to go on the path to a fusion reactor, you need to have long pulse discharges. And that is the aim of SST1. And hopefully we will do that.
Okay. Let me see, what is the next question? Okay, I think again, this is something that you already touched upon, but since someone asked, I'll just relate to you. So it says that unlike other partner nations in ITER who have, let's say, a roadmap for commercializing fusion, as you rightly mentioned, India still lacks a policy to let's say taking it forward. So how can we build that ecosystem so that we have a commercial fusion reactors can grow and sustain? And he also asks like where we are lagging, and I think you already answered that during the last part of your talk, and suggesting focus more on university things, which is something that you mentioned, rather than commercial programs. Right. So if you just can...
so we have to try on all fronts. As I said, we have to build up strengthen our base. We have to broaden our program, our scientific program. At the same time, also, by obtaining good progress in these areas, we will try to convince policymakers that this is something that we can do and we should do, and they should invest in us. Or on a global scale, it's quite obvious that fusion is the energy of the future, and everybody is investing in it. So, I mean, that is obvious for anyone to see. But now, we have to perform and establish definite goals and achievements in order to convince the government that we are capable of doing that. And this can be done in combination now with private industries and other players so that we can get a national policy in place. So this is what I think everybody is still trying, and we hope this will happen.
Okay, thank you. So the next question is about tritium breeding and how close are we to achieving self-sufficiency in the supply chain? I mean, what's the progress on tritium breeding?
Well, I really do not have detailed knowledge of that. I know that BRC DAE has a major program in this, which could be useful for our fusion program, but we have not yet attempted that here.
Okay. So the next question is that apart from, let's say, magnetic confinement fusion, there are alternative concepts which have gained momentum in recent times. And most of the private initiatives are based on those. So should we not diversify our efforts and explore other modes of fusion and not, let's say, put all our eggs on the same basket? So this is a question.
Okay. So apart from magnetic confinement fusion, the other major initiative is in inertial fusion, which is basically based around using intense lasers to implode a small pellet and infuse and induce fusion in that pellet. And I think Rajesh briefly mentioned that. And also in this, I mean, the most spectacular result in recent times has been what has been achieved in the US by the National Ignition Fusion system, where they actually obtained break-even in this laser fusion thing. But that is a totally different technology. And although India had earlier thought about investing in laser fusion, I don't think we took off in that direction. I think BRC had a small program so that Indore. But tokamaks are in the magnetic confinement, whereas tokamaks have been the most successful. And that's the reason why we're following that track. But there are variations to tokamak, which are like a spherical tokamak, or other configurations like the reverse wheel configuration or some variations of the pinch using various new stabilizing techniques that, as you correctly say, are being pursued by private companies, and they're predicting all these optimistic results. So that's something you can consider. But our mainline program is still devoted to tokamaks. So we would like to continue in that fashion. But we can encourage private companies to do this.
Okay.
Yeah, we have to keep watch on all these technologies.
Yeah.
And a lot of investment is also happening worldwide.
Right.
So, but in India, as Sid-Saab has explained, that Indian scientists are now quite matured in this technology, so they can adopt to any technology. Only thing is that we have to be alert and keep our global collaboration on, and at proper time it can be done.
Professor Sen, there is a technical question here that you mentioned about the radial and polaroid magnetic fields. So it's asked that shouldn't there be a non-circular current due to radial and polaroidal fields in the tokamak?
Non-circular current?
Currents due to radial and
so we are using a toroidal field.
Mm-hmm.
Which is generated by external magnets, mm-hmm. and we generating a poloidal field, which is by an internal current. And that internal current is a toroidal current.
Okay. So the next question is, what should be India's pathway to have sufficient inventory of tritium or enriched lithium to start a demo reactor?
Yeah, that is a long-term question and a very important one. So, yes, there are several ways that people are also thinking about doing this. I mean, using lithium, so which is you actually build a blanket around a fusion reactor, and this blanket could have lithium in it, and you want to optimize the design such that the breeding ratio is slightly greater than 1. Because then whatever tritium you use up within the tokamak or within the reactor is replaced by what you generate in the blanket. So that's the principle of the breeding ratio, and that's what you want to do. And people are experimenting with that. One can even do it on a smaller scale first to test out, in which you have a little test blanket put in a small device around the periphery, not to have the entire blanket there, and see how this works. So this is called the test blanket concept. And ITER already has that. So that's something we could also try.
Professor Sen, it all now depends on your time. Do you have time to take
No, I have time, but I've gone over your allotted time, so I hope.
No, because I see the enthusiasm of the people. There are a few more questions. So
sure, yeah, I'll be happy to.
Okay, so the next question is, what is the current progress in superconducting magnet research for plasma confinement? What is
Well, the latest development is this high temperature superconductors, which is something that was, the concept was developed at the university at MIT. And that's what led to this whole concept of this private company taking off and devising a much more compact tokamak. So in India, we have just started doing this. And as I said, BRC had already started a program on doing this. But we need to invest more and make progress in that.
Okay. The next person asks that, in my opinion, India has to start parallel research on low pressure plasma confinement. And what are your thoughts on that?
Low pressure, meaning?
Okay, I'll let the person just explain below, and I'll take the next one. So I think the next person asks that I think you mentioned that we have lacked some expertise capabilities in particular areas, and we need to bring back people who are formally trained. So what is the biggest roadblock what do you think for IPR to bring back people who are formally trained here and now working abroad, so that we can catch up and leapfrog faster?
Yeah, so for that we need a very active program or a larger program here where we can absorb trained manpower. That's the first requirement. And we can offer them jobs which are commensurate with their skills. So if you do not expand our program and get additional resources for doing that, this is not possible. But that's what we should aim to do.
Okay. All right. I think there are a few more questions, but I think due to lack of time, we have to bring it to a close. I may relay some of the questions to you over email.
Sure. Okay.
All right, Professor Sen, thank you very much. It has been an absolute privilege to have host you and listen to this illuminating session of yours. I think your session has provided us a much clearer understanding of where we stand and where we should go here forward from here on. I'd like to thank all the participants for your engagement and your insightful questions. So we look forward to see you again for our next session of Masterclass, which is scheduled sometimes in the middle of January. We will circulate the announcements and registration link during the first and second week of Jan, so stay tuned. Thank you, everybody, once again. Thank you, Professor Sen, for being with us today.
Thank you, Sumit. Thank you, Dr. Sharan.